What is up, everybody? Welcome to 8.5 trigonometric functions and the transformations with them. So if you hear construction or or that noise right there, if you hear that, then I am sorry. I cannot do anything about it. Um, except maybe lower the sound. I might be able to lower the sound of my voice, but that's really all I can do. So we're gonna get straight to the videos. This is the last time I'm going to go through these function transformations for the whole course. So make sure you get these, right? These are some of the most important stuff ever, because if you look at a function and you can figure out these, you're well on your way to being able to draw the function. All right, so don't abandon your pre-calculus or algebra 2 integrated math 3 skills when you go into calculus, because that will bite you in the back hard when you get to even the first section of the course, right? So anyways, we want to recall function transform. Let's use a simple function. Let's use f of x equals let's use fx equal to e to the x. So we want to transform up. We do x plus h, e to the x. So that will be e to the, let's say h is equal to 2. Wait, if h is equal to any number, right, it'll go to the left of it, because you need minus 2 to get 0. So if you do this, right, that's the regular function. Let's say this is 1. But then the modified function would be something like this, where this is e squared and this is 1 instead, right? If we had x minus h, that would be something like this, right? Where this is 1 and this is 1 over e squared, right? 1 over e squared. So that's how you transform, right? If you add something, if you add as constant, you go left, subtract, you go right. So we have the same thing for here, except that it's not in the function anymore, so it's not e to the x plus 2 anymore. It's something more like, this is e to the x plus 2 rather than e to the x plus 2, like that, right? There's a difference. This just moves the function up, right? You have the function moved up like this now, where this is just 1 plus 2, which is 3. And then if you have minus 2, that would just be like this. And there's this horizontal asymptote right here. That's the horizontal asymptote. The horizontal asymptote basically just says that it will never reach this point. However, at the limit to negative infinity, it will reach that point. So if it reaches negative infinity, the function reaches negative infinity, it'll get to 2. But nowhere in the domain will you see it get to 2. Right, so this is just going to be minus 1 plus 2, which is minus 1, no, minus 2 plus 1, which is minus 1. So move up, you move up, move down, you move down. That's plus h, outside, right? What if you had negative f of x? If you had negative just a function, then let's think about it. If you have e is equal to 0, if you have x is equal to 0, you'll get 1. But if you make that negative, you'll get negative 1. Right? Similarly, if you have x is equal to 2, you'll get e squared. But e squared, you make that negative, you'll get negative e squared. So that's like right there, negative e squared. And then if you put it at negative 2, it'll be 1 over e squared. And if you make that negative, it'll be negative 1 over e squared. So it'll probably be somewhere right here, negative 1 over e squared. So the graph will actually look like this. I'm spending a lot of time right now because I know that there won't actually be I know that this is the last time that we're doing this, and also know that it's going to be really important. So what about f of negative x? Now we have f of negative x, so that's different. If you put 0 in there, it'll just be f of negative 0, which is, well, just f of 0, which is the same. It's going to be 1. It's going to be 1. If you put e squared in there, you'll get f of negative e squared, which is e to the negative e to the negative 2, right? So, no, if you put 2 in there, not e squared, so that would be e to the negative 2. E to the negative 2 is 1 over e squared, which actually belongs somewhere down here. So for 2, this actually goes lower. This is 1 over e squared. 1 over e squared. But when you get higher, for example, if you put 2 in the function, if you put negative 2 in the function, you'll get e squared, which is somewhere up here. So the function actually goes something like this. Like that, right? So it's not going up, it's going down, it's decaying, it's exponential decay, right? What if we put f of ax? Well, f of ax is a horizontal stretch or shrink, and if we put 2x, let's say put 2x, so e to the 2x, now we have 0 is at 2, no, our 0 is at 1 still, so we still have 1 for 0, but this is a horizontal stretch, so it only stretches the horizontal. It doesn't mind about the vertical stretch. So our x is still at 0. But if we put 2 into the function, we actually get e to the 4th, which is way up, like way up here. But we're just gonna draw it right here. And if we put negative 2, it'll be e to the negative 4. So that's like way down here. 1 over e to the 4. So the function looks something like this. And it goes up way faster than all the other functions, right? These look like they go up fast, but this goes up way faster. So it is a horizontal stretch. It is a horizontal shrink, actually. So the higher the number of a, the more shrinkage. So because it's shrinking, it's kind of compressing through both sides, right? Imagine you have a hydraulic press right here, a hydraulic press right here, and then another hydraulic press right here. This is a terrible drawing of hydraulic press, I'm sorry. So if you crush the function in, the higher values of the function are obviously going to be closer to the center, right? The higher values of function are going to be closer to the center. This is a to the f of x. So we have our e to the x, the same thing, but this time if you put 0 in the function, you actually get 2. You get 2, right? And if you put negative 2, you'll get 2 e to the x, 2 over e to the x, right? So this is 2 over e to the x, now, or 2 over e squared, 2 over e squared, and then if you put it on the top, you'll get 2e squared, right? So this is the exact same function, but just multiplied by 2, whereas the other one exponentially increased. Oh god, I'm really sorry, I'm bad at drawing graphs. The other one exponentially increased. See, it goes from all the way from the bottom all the way to the top. This one just it has twice the growth, but it has the same growth as this, whereas this one has e to the x times more growth than this, right? E to the x times, and this only has 2 times the growth. So this is actually a lot more, right? That's kind of a review of exponentials right there. I spent way too much time on this. So what about the sine and cosine functions, right? That was what you were here for. So the sine and cosine functions, everything becomes a little bit more clear because we'll draw the sine functions from last time. Recall the sine function. We have something like this, right? Something like that. So this is 1, and this is y equals -1. This is y equals 1, right? So let's see what happens when we do our function transformations. So if we add 2, it just goes up, right? If we actually add 2 to the function, this now becomes 2, and then we have a line y equals 3 and line y equals 1. If we subtract, it goes down. If we add it inside the function, let's say sine of x plus 3, right? Or sine of x, actually let's make it easier. Sine of x plus pi, right? You guys might be thinking that makes it harder because it's pi, it's irrational. But it actually makes it easier because look, we have this right here, right? We have this. It goes up, it goes down, it goes up. That's the regular sine function. But the sine of x plus pi moves it right. No, I mean moves it left by pi values. So you actually have like this. You actually have this type of function. Something like that. You'll have something like that instead, right? Where it's still y equals 1, and it's still y equals negative 1. And this actually is also the graph. This is also the graph of minus sine x. It's the same graph of minus sine x. Because this, okay, I'm going to draw the original function right now. This is the original function. I'll do it in green. Right, the original function is like this. So minus sine x means everything that you get will be negative. Everything that you get will be reflected upon the y-axis. And it works, right? Everything that I get is reflected upon the y-axis. And this is actually also the exact same graph of this. Since it's an odd function, sine of negative x is equal to negative sine x is equal to sine of x plus pi. And it's also the exact same graph of this. Right? It's also the exact same graph of this, x minus pi. Right? This just becomes pi, this just becomes a minus pi minus x. And it's the exact same graph, right? All of these graphs is this. But whenever we move it a little bit, to the right or to the left, it's called a phase shift. And you don't need to know this, because I really don't know why you need to know. The book says it's called a phase shift. So it's basically, you basically move phases. You move the graph for a little bit, and that's what it's called. It's called a phase shift, right? If we do sine of x plus pi over 2, actually no, first of all, yeah, if we do sine of x plus pi over 2, what do we actually get? Oh no, sine of x, let's do sine of x minus pi over 2. We'll move the graph a little bit this way. Right, we'll move the graph a little bit this way, so it becomes like something like this. Right, what does this graph remind you of? If you watched the previous video, you should know what this graph is. This graph is the cosine function. Right, so it even works with graphs. I proved to you why sine theta minus pi over 2, or sine theta minus 90 degrees, is equal to cosine. A few, not proved, but like I showed you why it was the same thing about a few lessons ago. And this is another way you can view it, right? Sine x minus pi over 2, you just shift it by 90 degrees, and you get cosine of x. Right? You shift it the other way, you'll get minus cosine of x, because we've already established the kind of why it happens, right? But it doesn't work all the time. If you have sine 2x or sine 2x, you can't minus pi, and that would be the thing. You actually have to minus pi over 2, because I'll explain to you why later, or might not. Okay, these two are actually pretty useful to know. So what's the period and what's the amplitude? Right, so the period is the amount of time it takes to go through one cycle of the function. So what's a cycle? Well, a cycle is one time that it goes up and it goes down and it touches the middle. So this is a cycle right here. It goes down and then it goes up, and that's a cycle right there. So that's the period as well, right? And in a sine function, when does it hit 0? Well, it hits 0 at x equals 0. It hits 0 at x equals pi, and it hits 0 at x. This is minus sine x, by the way. It's minus sine x, but it still has the exact same period. This is 0 at x equals 2 pi, right? So 0, pi, and 2 pi. And we've already established that this function right here, x sine of x, has period is 2 pi, right? Sine of x has period 2 pi. What's the period of sine 2x? Well, sine of 2x is, we already know the values that sine of x is going to be 0 at. So sine of x can be 0 at x equals 0, so we still have the x equals 0. But sine of x is actually going to be 0 also. Sine of x is going to be 0 at x equals 1/2 pi. And the reason why sine of x is equal to 0 at x equals 1/2 pi is if you multiply 1/2 pi, multiply by 2, you'll get pi, regular pi. The sine of pi is 0, right? And it's also 0 at x equals pi, 3/2 pi, 2 pi, 5/2 pi, 6 pi, not 6 pi, 3 pi, 7/2 pi. It's 0 on all of those. And it's 0 every 1/2 pi. So if we take 2 of those zeros, which is the time that it goes up and down, you'll get pi, right? So 1/2 pi plus 1/2 pi is pi. So the period is pi. And the general formula to find the period is actually 2 pi over coefficient of the x variable, right? Coefficient of the x. Let's say, okay, in sine a of x, sine of ax, the period is equal to 2 pi over a. So if a is equal to, I don't know, nasty number 334 over 5, then the period would be equal to 5 pi over 17. Right? Every 5 pi over 17 would be the period. If I calculated that right. Yeah. Every 5 pi over 17 would be the period. That's a really fast period. Right? The amplitude is the height of the wave. So the amplitude is pretty easy. Right? The amplitude of this wave is the distance from the center, or the distance from the center of the wave to the top, which is just 1. And let's say we have a different wave. Let's say we had 4 sine of x. Right, the amplitude is really easy to figure out. You guys, if you guys took, I don't know, trigonometry in your geometry, you might be able to figure this out quite easily, because the amplitude is just this number. It's this number. That's the amplitude. Right? It's the absolute value of that number. So if we had b sine x, it'll be the absolute value of b. And that would be the amplitude. So if you had, that would be something like, it would be something like this. Notice how it still has the same period. Right? It still has the same period. It just has different amplitude. Still has the same period, still goes through pi, 2 pi, minus 2 pi, and does one cycle in pi and 2 pi. Does one cycle in 2 pi units. But it's just a little bit different than period. Right? So if you had a high period and a high amplitude, your wave would go really, really fast, really tall and really fast. That'll make a loud and a high-pitched noise, which is definitely not pleasant at all. So I wanted to graph these. It's 20 minutes already. Should I even graph them? I'll graph them. We'll do 2 parts to this. So it'll be 8.5 trig transformation. I'll probably add more. I'll probably add more problems to solve. So we have tan of 2x, and we've already established the graph for tan of x. And the graph for tan of x is something like this. Yeah, with the asymptotes every single time, right? That's the graph of tan of x. Right there. But what does the 2 do? Well, the correct answer is the 2 doesn't really do anything, right? The 2x in there is actually no, I lied. The 2 does a good amount of stuff, right? I was thinking of 2 tan x. The 2 tan x doesn't really do anything. 2 tan x, the graph would just be like something like this. Oh, sorry, that's a terrible. Yeah, the graph would just it'll just look a little bit taller, and it won't really do that much, right? That's how the graph would look like if it was 2 tan x. But tan of 2x is quite crazy, and we want to look at the sine. We want to look at the cosine function because we have sine x over cosine x, right? In this case, it's sine 2x over cosine 2x. So when x is equal to 1, well, we want to find values when cosine of 2x is actually equal to 0. And the reason why is we want to find undefined values. So when is cosine of x equal to 0? Well, cosine of x is equal to 0. We look back at our unit circle. It's pi over 2. It's pi over 4. No, it's pi over 2. It's 3 pi over 2. It's 5 pi over 2. It's 7 pi over 2. So cosine x equals 0 at x equals pi over 2, 3 pi over 2, 5 pi over 2. And if we extend this to the fact that cosine 2x is equal to 0, we'll actually get cosine 2x equal to 0 at, let me move this line down a little bit. We'll get cosine 2x equal to 0 at x is equal to, well, just half that, pi over 4, 3 pi over 4, 5 pi over 4. So the actual graph, the final graph, will look like this. We'll have that, and then we'll have that, and then we'll have that. Okay, I'm just drawing these lines now. I'm really bad at drawing graphs. I'm really sorry. We'll have that, and then we'll have oh, damn it. We'll have that, and we'll have that, and then we'll have that. Right? It's gonna appear twice as often. It's gonna appear twice as often. Right? And all of these are asymptotes right here. Right? They're all asymptotes, and because the reason why it appears twice as often is because cosine of 2x is zeroed at pi over 4, 3 pi over 4, 5 pi over 4. That means the graph's undefined at pi over 4, 3 pi over 4, 5 pi. It's an infinite discontinuity. It's not bounded at the points, right? The top and the bottom. So therefore, this is the graph that you get, right? And that's gonna be it. That's gonna wrap it up for today's lesson. I did not think that this was going to be 2 lessons long, but it looks like it is going to be 2 lessons long. And we have the next lesson. We'll go through applications of a lot of applications of trigonometry. It might be a 0.5b, it might be a 0.6. I'm not sure, right? Because I do want to get through all of this. It might be an 8.5 plus 8.6. So if you want to see it, if you want more of these lessons, just press like button. I really should start doing stuff in my other channel, but I'm just lazy, and that's it. And so I'll see you next time for applications of trigonometry.